All right, just to finish up where we were talking about polarization of charge or charge polarization, or the inducing a charge or an induction of charge. Basically, if we have a atom like this, you have electrons spread around the nucleus with the protons. You have equal number of positive and negative charges. So it's this shaded area just represents the area where the electrons are. Okay, if we bring something that is positively charged near this, we see a change start to take place. Okay, this positive charge begins to repel the nucleus, which is positive, and so it scoots away from the charge, and the electron cloud, or this group of electrons around it, are attracted toward it because it's the opposite charge. And so we end up with the atom having a negative charge on this end of it, and since the protons in the nucleus has shifted over here, we have a positive charge over here. So we say that we have induced a charge, even though there's still equal number of electrons and the protons in the nucleus. So the net charge is zero, or the whole atom is neutral. But since we pulled more negatives over here, it makes it more negative. Since we repelled the nucleus over here, it makes this side more positive. And so that's why it's also called charge polarization, because now we have a positive and a negative pole of the atom. This could also happen to objects, larger objects. For example, if we rub any balloon on our heads, it would rub off electrons, which means that the balloon would have a negative charge. If you bring it to the wall, the negative charges would attract positive charges and therefore make it stick. They're attracted to each other, and that would make the balloon stick to the wall. Okay, the electrons, or the negative charges, would be repelled. The wall still has a net charge of zero because it has the same number of positive and negatives, but this side has been polarized to be positive and this side has been polarized to be negative. And so we would say that we have a charge polarization, or we have induced a charge. We've forced this side of the wall to have a positive charge and this side to have a negative charge, just by bringing this other charged object, in this case a negative charge, balloon, to the wall. Electricity that we've talked about so far is known as static electricity because it's not going anywhere. Okay, when we rub the silk rag on the little rod here, it gives it a charge, but that charge is not flowing or going anywhere until you touch something with it. It's like if you rub your feet on the floor, you build up a negative charge, but then until you touch something, it just stays on your body. Until you touch something, then it flows into them, and it flows quickly, and then it's gone. Okay, same thing with balloons and stuff like that. We rub them. So these are all static electricity. In general, we think of static electricity as not being very strong. This was the first electricity that was investigated, and needless to say, it didn't bring around a lot of industrial revolutions because it's a fairly small charges. They only build up in one place, and then they're quickly discharged, and then everything goes back to even, and there's no charge difference anymore. So it really doesn't make a whole lot of impact. Okay, but that's not to say that static electricity is not important. For example, back in the old day, 1700s, 1700s, British warships had what they call powder monkeys, that talked about in your book, and basically their job was to run around the deck, bring powder to the guns and so forth, and they could build up enough static electricity between their shoes and the floor of the ship that they could actually ignite the gunpowder and cause explosions. So it was made, they were required to go barefoot because there was less static electricity that way. Now, static electricity can still be a problem. People working on circuits and transistors and small chips and various things have to be very careful. They try to wear outfits that have low static electricity. They may have little ground wires going from their cuffs down to the ground to leak off any charge that builds up, because the smaller the chip, the smaller the circuit, the amount of electricity goes into it to begin with, the static electricity could cause damage and destroy those circuits. So it still can be very important, but it's not what we think of for turning on light bulbs in our home or keeping a city in electricity. Where electricity has a business effect is when we can make it flow, and anytime we have electric flow of electricity flowing, we can call that a current. Okay, so an electric current is just the flow of the electric charge. Once again, you think of what part of the atom is going to flow. Okay, go back to our atom over here. Protons, the positive part, are in the middle. They cannot leave. They're bound tightly there, so they cannot go. They're held together with the neutrons with nuclear forces. Okay. It's only these outside electrons. These can be called valence electrons. Okay. Sometimes they may call them conduction electrons because these are what conduct electricity or conduct heat for that matter when we get to that. But they can be called conduction electrons, or you may hear them called valence electrons. All right. So usually you hear conduction electrons would be more likely if you're talking about electricity or heat, but valence electrons is what we usually call them in chemistry. In chemistry, this will be very important to get atoms having charges, positive and negative, so we can put them together and make compounds. And basically, everything in the world is made out of some kind of compound or atoms. So that will be very important. But for now, let's just say it's the electrons that are going to move, only the ones on the outside layer. Now, this only has one layer because it's helium. Others have several layers. It's only the outside layer, the very outside layer of electrons, that can actually move around. Now, electrons, depending on several things. One, how big is the atom? The bigger the atom is, the farther these electrons are from the positive nucleus. So they're going to be held less loosely, or less tightly, excuse me. They're going to be loosely held, okay? It can have to do with size. It can also do with the number of protons. The smaller the nucleus, and they have less of an attraction, but they're also closer. If you get farther away from it, then you have less. So it has to do with the size of the nucleus, how many protons you have pulling on it. You have how far are the electrons away from it. But there's also metals in general. We'll talk about metals and nonmetals in the periodic table. But the left side of the periodic table, which are metals, are basically very good conductors, and one of the reasons for that is they don't really hold on to their electrons. In a piece of metal, you have a bunch of electrons all crammed together, and their electrons just kind of float from one to another. Okay, this would be kind of like mothers who go down to the park with their kids, and they just kind of let their kids all mix together and whatever, and they don't really worry about where their kid is or where someone else's kid is. They just kind of keep an eye out for the kids that are around them. Okay, that's kind of what the electrons in a metal do. And since they can move from one to another without anyone worrying about it too much, they flow easily. We say they would flow, okay? And since they flow, then when they flow in the same direction, you would have current. Now, if they were just randomly flowing, the odds are they're going to go in random directions. Some might flow this direction, some would flow this, and so on the average, you don't have a net flow or a net charge of the atoms. However, if they all begin to flow in the same directions, then that is a current. Okay. Now, a current, we'll talk about this later, but a circuit has to be in a complete circuit, which means it has to connect back around. That's because if all the electrons start flowing this direction, eventually all the electrons end up over here, the valence ones, the ones on the outside edges that can leave, and you don't have any more over here, and there would be no way they could keep flowing. To just sustain the flow, they have to keep returning back again to the other side. And so this is what happens and why you have to. All right, so how can we make electricity flow in one direction? Why do we want to make it go from one direction to another? Well, if we think about water, we have to have a hill or something like this, and water will always run downhill. Okay, it has more potential energy up here, gravitational potential energy, and gravity pulls it down, and so it wants to flow down. So we'd say that there's a type of pressure difference. Other times when we have a pump that is pumping water through, okay, the pump creates a pressure difference. As it pushes water in one end of the system, then that will push water around throughout the system. Okay, and so it's creating pressure, if you will. Okay, water pressure. All right, and so as your water is flowing out over here, you have the pump filling it back up and creating this high water pressure here that will keep it going. Okay, and so it can continue to keep pumping in and out. Okay, now the question is, that's great and good for a pump, but how does that happen in electricity? Well, basically, this is a very general idea, but basically, just like the water keeps pumping water and putting pressure on it, and then it comes back over here, and so it's always going from higher pressure to lower pressure. Okay, the voltage source, a battery usually we think of, okay, this is creating a pressure of electrons. There are chemical reactions that are going on here that are building up electrons. Just like you have water building up here where the pump is putting pressure on it, you have this battery is producing electrons, which builds up a higher pressure of electrons here, so they flow from high pressure to low. Okay, and eventually, though, if these chemical reactions quit making electrons or producing electrons, free electrons flowing around, then eventually we say the battery is dead. Okay, so a battery is the pump, if you will. It keeps the pressure by creating using chemical reactions to create free electrons, and as these free electrons build up over here, it will flow around from the negative pole over here to the positive, and so it will create a circuit, and the water will flow around that circuit, or rather the electricity will flow. Sorry, I got my example mixed up there. But now the question is, what is this pressure? Well, this pressure is what we call voltage. Okay, so voltage is basically the electrical potential energy. Okay, the electrical potential energy that builds up like in a battery and causes the pressure difference, if you will, or the different level of electrons that causes the electricity to flow through that. So if you think of it, it could be kind of like thinking of just like when you push a spring closer together. Okay, when you push it closer together, it has the potential now to spring back. Well, if we have a bunch of electrons and we squeeze it closer to all the other electrons, now since they repel each other, it has the potential to spring or move as well. So as you build up these electrons that are getting pushed together, that gives them the potential energy and the pressure, if you will, that causes them to flow through the circuit. Alright, now just like water, in order to continue to flow, needs a difference in height where it can, gravitational potential energy can pull it, or pressure, like a pump putting more pressure to keep it flowing. You have to have something that keeps up the pressure, and we said that's the battery. A battery builds up those electrons and causes it to flow. Notice the voltage is the pressure that causes the electrons to flow. So through a wire, we have electrons flowing through the wire. We don't say the voltage flows through the wire. The voltage is the difference in pressure that causes that. If you look at a plug, you always have at least two plugs. Very big objects, you have a ground for safety, which will take, in case it short circuits or causes other problems, it'll take it to the ground. We'll talk about that later, but you always have two plugs. And if there's no voltage difference between the plugs, then nothing happens. But if there is a voltage difference when you plug it in, then the flow through to your appliance, back, and come back through the other prong and create a complete circuit. Okay, so it will not flow unless there's a difference in voltage. Okay, just like I have a different pressure with the water or a difference in height of the water. So technically that means if you take a bird and he lands on a highline wire, even if it's bare wire, it's carrying electricity, as long as the voltage is the same in both feet, then there's no difference. Okay, but if he touches a ground or some other object that has a low voltage, then it's going to go from high voltage through his body and down to the ground. Okay, and that causes, and will fry the little sucker. Okay, a lot of electrical poles had to be changed in some areas because a lot of birds, especially eagles and stuff, would land on them. As long as they're on the wire, they're okay, but they would reach out and they would touch the post or other things, parts of the wire, the telephone pole that were grounded, and it would shoot electricity through them and it would kill them and fry them. And they kind of frown on that, especially when it was an endangered species and all. So there we go. All right. Now, so a current is what causes it to flow, and our current in the United States is usually 120. Okay, you talk about what's the voltage of your plug or whatever in your house. Usually the voltage is 120 in the United States. In Europe it's 220. Okay, we also have 220 for some outlets like the washer, dryer, things that require a lot of energy to run. Okay, but if you go to Europe or something like that, you have to get a adapter or converter thing that basically transforms or steps down the voltage from 220 down to 110. Otherwise, when you plug your things in, they will get more electricity than they're built to handle, and you would have a lot of problems, and if it didn't just destroy them. So very important that you should have the right voltage coming into your stuff. All right, we'll stop there and we will start with resistance in the next video. So resist your temptation to not watch it, and we'll see you there.